Well, welcome to this morning's plenary session. Several announcements we need to make about the meeting. And next slide. The first is code of conduct. Just a reminder about code of conduct. And one thing in particular to point out is if you're outside meeting rooms, please try to keep it a little quiet. And it's great to talk, but it's been a little noisy, which is okay, but keep it to a dull roar, please. Next slide. We want to point out especially, we want to thank the COCUS sponsors, especially National Science Foundation, the Department of Energy, for supporting, that program. A really great program, lots of support for our students. Next slide. I want to remind you that the exhibit is open now. It was open last night. It'll be open all day today. All food will be in the exhibit hall from now on. And just some photographs of the event last night. In terms of DEI, we want to make an announcement that back to popular demand, Chris will be running another yoga session today. That'll be, I have to get the details straight, 5:45 in the Omni. And check your social media for all these things because it continually changes. And now we're going to talk about the Emmett Award. We heard a little bit about this yesterday. Next slide. One thing to point out is that Emmett was a good friend of Linus Pauling, if you remember that name, and elected to the National Academy of Sciences as well. Okay. Next slide. You can see several award winners here. I think we saw this yesterday as well. Congratulations to Yuriy. We're looking forward to your presentation real soon. Next slide. Please welcome to the stage Chris Jones.
Good morning, everyone. For those of you who don't know me, my name is Chris Jones. I'm the Vice President for the North American Catalysis Society, and I'm very pleased to have the opportunity to briefly introduce Yuriy Román-Leshkov to you, who's our 2024 Emmett Award winner. So Yuriy was born in Mexico City. His father grew up in Mexico. His mother is from Belarus, and he moved to the U.S. in 1999. So he came to the U.S. As a transfer student to study chemical engineering at the University of Pennsylvania. He graduated from the University of Pennsylvania in 2002 after earning his bachelor's degree. At that point, he worked for 1 year as a materials engineer in the auto industry, and then ultimately decided he wanted to return to graduate school to earn his PhD. So in 2003, he began his graduate studies at the University of Wisconsin-Madison, working under the guidance of Jim Dumesic. He graduated in 2008 and then moved west to Pasadena to undertake postdoctoral studies under the guidance of Mark Davis. He started as an assistant professor at MIT in 2010, was promoted with tenure in 2017, became a full professor in 2019, and was awarded a professorship most recently in 2021. So Yuriy is a very active researcher in catalysis. Focal points for him are zeolites, biomass and plastic conversion, small molecule activation, catalyst design, and very recently he's focused on catalysis via confinement effects and electric fields. He's won a number of awards and honors, the most recent obviously being the important Emmett Award from the North American Catalysis Society, but he's also been recognized by the Chemical Reaction Engineering Society with the Rutherford Ayres Award, and he received the Bob Augustine Award from the Organic Reactions Catalysis Society, which is a sub-society of the North American Society. Yuriy's very engaged in professional service and leadership as well. He's an editorial board member for 3 different journals from 3 different publishers. He served as the chair of the Lignin-Gordon Conference in 2022, and he was the chair of the New England Catalysis Society, again, a part of the North American Catalysis Society, from 2015 to 2017. So I've been fortunate to know Yuriy since his days as a PhD student, and one thing that if you know Yuriy, you know that he always has a smile on his face. So he's got a boundless enthusiasm for catalysis, he's got an infectious energy, and it really makes him a joy to be around. That energy is important because he has a big family. He's a father to 6 kids, which means he is mentoring people 24/7. Both his roles as a researcher and mentor and a family man are important to him. I believe that you will see his enthusiasm very easily when he comes up to the podium to share with you his recent research results. And to this end, I'm pleased to invite Yuriy to the stage and offer my congratulations for his selection as the 2024 Paul H. Emmett Award winner. Congratulations, Yuriy.
All right, well, thank you very much, Chris, for the very nice intro. And I want to start by thanking the North American Catalysis Society and Grace for sponsoring this award. And, I gotta say, I am tremendously honored and humbled and quite honestly still in disbelief that I'm receiving this recognition. It's really amazing. And, I received a message shortly after I got the email from Jingwan from Chris Jones. And in that message, a part of it that really stood out to me was that he told me, listen, your career is going to pass by in a heartbeat. So make sure to pause and think about what is it that made you kind of get here? What is going on? And I did, and it really made me realize that it would be impossible for me to be up here if it wasn't for a group of people that have been in my life all throughout. And I want to start by thanking them. I want to start with the current team I think my group is right here in the middle. And I want to tell you, thank you for the amazing enthusiasm, curiosity, love for science that you have. And you really inspire me. And this is the reason of why I come to work every day. So I really appreciate that. And I also want to say thank you to the people that already went through the group, from the graduate students that are here, postdocs that went through the group, as well as visiting scientists, undergraduate students that really took, especially in the very beginning, took a risk, a leap of faith to join the group when I was just starting up. And it's something that I'll always be grateful about that. Then we have I've had the privilege, to work with just amazing collaborators, people that have challenged me, people that have pushed me to expand my scientific boundaries and go into areas that I would never have imagined I would go into in terms of the science that we do. And it's been really an amazing journey to do this with them. Also, I've been very lucky to have amazing mentors. And these are people that not only have provided feedback and help science-wise, but also have helped me navigate this entire journey in academia. And I am very, very grateful to them. I had the chance to spend a year in Valencia for my sabbatical, and I got to know Avelino really well. And he always would have, if you know him, he has all these phrases all the time. But one of them that always stuck to me, he would tell me, Yuriy, listen, this profession is a marathon, not a sprint. And you can go as fast as you want, and at some point you will finish. But the important thing is that you have to enjoy the journey, you have to enjoy the race, so make sure that you do it at your own pace. And I think those are very, very important words for us to remember. In addition to that, I don't know what it is about the PhD program or the postdoc, or when you're starting a group, maybe it's kind of like all the stress of doing this work. But in addition to being conducive to making science, it allows you also to forge very strong friendships. And I'm tremendously fortunate that I have a really strong group of friends that I've known now for many, many years that have been there always in the good times and in the bad times. And I think creating this support network is important for us to be able to advance. So I really appreciate them. And then I want to talk about two very important people that really shaped the way we do things. And I want to start by talking about Mark Davis, he was my postdoc advisor. He took a risk, of taking me in when I was applying for postdocs. He didn't have funding, and he was able to somehow find a way to bring me in. And it really changed the way I think about catalysis. So he taught me a lot of things about catalyst synthesis and zeolites. And if you know him, you can kind of like witness this brilliance and this intuition on how to solve problems in a very unique way. And to me, that has always been very inspirational. And then there's Jim Tumesic, just an amazing mentor. So he always has done just always breakthrough science. But what was always very interesting to me is that he's just such an amazing individual, such an amazing human, and he likes to help you out. He will always be there. He's an amazing mentor. And I learned a lot from him during the PhD. But in thinking now back, I think I have learned much more after I left his group, because now I'm able to recognize the nuances of how he approached the problems and everything that he did behind the scenes to support his team. And to me, that is very, very special. And an element that I always admired about him is that he was able to combine things from very different fields to kind of look at the problem in a very different way. And I think that is something that we try to apply in my group now. And I hope that in the science that I'll show you, you can see some of those elements on kind of like how you combine things from different perspectives to try to approach old problems, new problems, just in a different way. Then I'd like to also thank MIT for a lot of the seed funding that helped me get started on some new ideas, as well as federal agencies, companies that fund the research and fuel kind of like this enterprise that we have on making science. And with that, these are all the elements, no pun intended, that make, of why we're here today. So thank you, everybody. On Sunday, we had a workshop for the Journal of Catalysis, and Studio Linek, he was in the table, and he mentioned that catalysis is at an inflection point. And I think that is exactly right. We're facing some very interesting challenges today that we have to now recognize and implement new ways of thinking about catalysis so that we can solve them. So we are starting to see many more, or an input of renewable electrons. We're going to potentially electrify the entire light-duty vehicle fleet. And that means that is going to have some very deep repercussions as to how conventional refining will work and what the outputs would be. We are facing a crisis in terms of emissions as well as pollution from plastic waste. So we need to figure out ways of handling that. And for those sectors that we cannot electrify, we need to figure out new ways to decarbonize them, or actually using sustainable carbon sources so that we can do it. And this is where biomass or maybe CO2 conversion come into play. And catalysis then will be at the center of this all. And several of the projects in my group have to do with, well, how do we address some of these sustainability challenges? So when we work in an experimental catalysis group, then we have a few handles that we use to solve those particular challenges. And we use models, and we try to figure out on how to synthesize a catalyst that will be able to promote a particular reaction. And now, more recently in the group, we have spent quite a bit of time of thinking, well, what can we do beyond the active site? What can we do in terms of altering the environment near the active site so that we can accelerate these reaction rates? And today, what I want to share with you is 3 short stories on how we think about that. One of them being on how do we do cooperative catalysis so that we can have 2 functions doing something that each one of them independently cannot do. The idea of how we can exploit confinement in liquid phase catalysis to accelerate rates, and then how we can think about electrostatics and electric fields also to modulate thermochemical catalysis. And with that, I'll start with the first story. And this is a project that we had never worked on metathesis before. We worked on this for about 4 years. And this is work that was led by Terry and Rand, people in the group. And we started a collaboration with Christoph Koppere, with Zach Bergson, who is the postdoc working on this. And this is a very interesting reaction. So if you are familiar with olefin metathesis, this is the interconversion of functional groups surrounding a CC double bond. It's thermoneutral, very high selectivity, and it sees applications in a wide range of areas. So we use it, for example, for gas interconversion, polymerization chemistry, pharmaceuticals, and here you have a picture, for example, of the Lumos OCT unit that we can do it for large-scale, propylene production, for example. In 2005, Grob, Schrock, Chauvin were awarded the Nobel Prize in Chemistry for elucidating the mechanism for olefin metathesis using these organometallic catalysts. And in the course of these 3-4 decades that we have studied these homogeneous systems, we have understood very well how the mechanism works. And because of that, we have this tremendous flexibility in terms of the synthetic flexibility that we have on making those particular catalysts. Now, on the other hand, when we're looking at gas phase, high temperature chemistry, we are using standard incipient wetness supported catalysts. So tungsten at high temperature, molybdenum oxide, and in some cases, rhenium oxide as well. And for these systems, even though they're stable, and this is what we use at high temperature, there's still a lot of open questions as to how do they work. And this is where we started this particular project. So if you look at the homogeneous side of things and you look at the Chauvin mechanism, we know that alkylidine species are the ones responsible of initiating the catalytic cycle. Now, when we work with a heterogeneous catalyst, we have supported metal oxide catalysts, and something has to happen in between the initial state of the system for it to enter the catalytic cycle as a metal alkylidine. And there's multiple hypothesis as to how this happened. It appears that perhaps there's a reduction involved from, say, if we were working with tungsten, from tungsten 6 to tungsten 4, and then some kind of oxidative addition event that allows you to enter that side. But how does this happen? There's a lot of open questions regarding that. We have never observed the carbines actually spectroscopically. It's very difficult to see them during reaction because of the high temperatures, for example, in tungsten. And there's very few reports or very inconsistent reports as to how many sites are there. So for molybdenum, for example, people say that it could be 1%, maybe 10%, and these numbers vary in the literature. So there's no clear way of doing this. And then when you look at the apparent kinetics that people report, you always get orders, usually, in the about 1.5 to 2 on the reactant. But if you look at the Chauvin cycle, really the order of the reaction should be somewhere between 0 and 1, depending on the conditions. So why are the kinetics not fully following what we observe experimentally? And that's kind of like how we started. And we began our investigation with 2 catalytic systems. So we were working with the standard industrial incipient wetness type catalysts supported on silica. And then we have what we call the single-site catalyst, using organometallic chemistry to graft single sites onto the silica support. And then we spent quite a bit of time to carry out these reactions in a rigorous way. For those of you that have worked in metathesis, I feel for you because this reaction is tremendously sensitive to impurities in terms of oxygen, in terms of water, and you have to be very careful to run the reaction well so that you can get reproducible data. And when we run this, in this case we're looking at propylene self-metathesis, we see that we can obtain or reproduce what is usually reported in the literature. So orders close to 2 on propylene and activation energies that are in the order of 150 kilojoules per mole. When we run now the backwards reaction, so in this case this is ethylene plus butene going to propylene, we now obtain also orders that are in the about 1.5 or so, but the 2 orders on the 2 reagents are different. So for ethylene we get about half order, whereas for butene we get an order of 1. And to us, that was a curious phenomenon. So then we carry out another experiment that threw us off for a little bit. So imagine we're running propylene self-metathesis. And then we added butenes to that. So we added some of the product to it. And in this case, we're expecting to suppress the rate just because of altering the equilibrium. But what we observed was the opposite. In fact, we were able to increase ethylene production when we added some of the butene. And that started us with this hypothesis that maybe there's a second event happening in addition to the Chauvin cycle. So there must be something going on in terms of butene participating in the side generation, going from the initial state all the way to the active state of the catalyst. So we painted a picture like this, now with two cycles running concurrently, one of them working on side renewal, and then eventually there will be some kind of side decay that brings the catalyst from the active state to the resting state. However, if this is the case, and now we have two independent cycles going, that means that we can potentially kinetically decouple them. And that gives us an opportunity to hijack one of them and be able to perhaps increase the rates that way. So that's what we tried to do. The idea would be to now add an olefin into the system that would not undergo metathesis, but that would help you in the side generation side of things. If you look at the kinetics of how they would look, then you see that you would be able to recover the apparent kinetics that people observe in the literature if you consider now these two cycles. So you have the Chauvin cycle contribution, and then you have the kinetic contribution of the side formation and decays. And if that is the case, then your rates will be proportional to how good of a promoter you add for that particular system. Your orders should add up between all the different parts, the promoter taking care of the side renewal, and then the actual olefin that undergoes metathesis would be the one that is in the Chauvin cycle. And in the end, these promotions should lower then the apparent activation energy because you are increasing the rate at which you generate those sites. So we went ahead and selected a set of olefins. This would be a cyclic olefins that were 1,1 disubstituted without heteroatoms. And we're starting to look at increasing the electron density on the double bond. And as you can see on the bottom of the screen, when we worked with ethylene that has, say, 4 methyl substitutions, so something that is a very electron-rich olefin, we got promotion rates where we increased the reaction rate 5-fold or up to an order of magnitude. And we started to now investigate this in more detail in flow. So as you can see here, we're now flowing together at steady state our propylene, as well as this, what we call 4-ME for the promoter. And you see that we can get up to a 30-fold increase in the rate this way. And this, regardless of the catalyst that we use, so we see this phenomenon, for example, for tungsten oxide as well as molybdenum oxide. When we now run our kinetics, we see that everything starts to fall into place. What I mean is that when we run now on the promoted case and we take a look at the reaction order of propylene, we see that now we get orders that are less than 1 on propylene and activation energies that are much lower in the order of about 120 kilojoules per mole. And then the promoter is the one that picks up the rest of the order in the overall rate. In addition to that, the promoter is not consumed in this case. So we have done some in situ spectroscopy, and we do observe that these promoters help you in increasing the amount of reduction that you get in the system. So that means that you can reduce that tungsten or molybdenum species a little bit better. But in addition to that, there's a second thing that occurs here in that there is a promotional effect in terms of having a Bronsted site close to your metal center. So whenever you deposit these oxides on silica, you have this induction effect that eventually creates or generates very strong acid sites next to the molybdenum or next to the tungsten. And then from very detailed work by Christoph Koppere's group at low temperature in liquid phase metathesis, they have shown that when you have protons surrounding the center, you can actually accelerate it, you can promote this formation of the active sites. So we ran some calculations and we started to take a look at, well, do we have a proton-assisted mechanism for the system? And in this case, the resting state of the catalyst is state 3 here in the center of the group. So it's an alkyl tungstate, a tungstate alkyl species. And the way you get it is by doing a hydrogen transfer to that pi bond in the state 2. And you can get that, again, assisted by the proton that is close by. Then to get to state 4, then you do a hydrogen abstraction, and that's how you get your alkylidine back there. So then when you do the calculation in the absence of that proton-assisted mechanism, you see that the apparent barriers are much, much higher than with the assisted. So that's kind of like our hypothesis. So we went ahead and did some solid-state NMR, and we see that indeed, we have some very strong acid sites next to our tungsten species that are able to protonate pyridine, for example. And we know that for that to happen, you have to have strong Bronsted acidity that you cannot get usually with just salinols. In addition to that, when we run now the two-dimensional NMR in the presence of our promoter, we see that we have a lot of alkoxides present that you, again, do not get if you do not have the promoter, or you do not get if there's no salinols around the site. So we think that then these alkoxides played a very important role in terms of how you create the sites. So we painted now a different mechanism of how we think this is happening. So in this case, you have the Chauvin cycle in black, and then in blue is the proton-assisted step, proton-assisted metathesis step, right, where you make your metal alkyl species and eventually those decay. And here, what we think is happening then is that these promoter olefins form alkoxides, and those alkoxides now have hydrogen atoms that are much more easily transferable to the metal center. And because of that, we're able to now hijack that cycle and create those sites much easier that eventually generate your resting state and for it to eventually become the metal alkyl species. And what is interesting about this is that if this reaction pathway is indeed going through this, you have now a new handle to increase the number of sites that you have at will, which allows you now to perhaps titrate the system. So we ran some experiments in this Sitka type setup, where we now run at steady state, do a switch into a different olefin and try to track the products, and then do sort of a del plot analysis so that we can extrapolate, say, to infinite space-time. And from there, we can actually start counting what happens with the sites in the presence or in the absence of promoter. And we see that for supported molybdenum oxide, we increase the sites from about 15% to 50% in the system. For this SOMC catalyst, the single sites, we can get up to 80% of the sites being active. And even for tungsten, we have never found a site count on tungsten in the literature. We're able to see that we can get about 16% of the active sites there. So to us, this was very, very exciting to do and allows us to perhaps be able to refine a little bit better what systems do we work with. Not only that, but working with Christoph at ETH, they have some amazing NMR instruments. And if you have ever tried to do molybdenum NMR, it's very challenging. It's a tough nucleus to work with. But if you have a high field magnet, you might be able to actually differentiate different types of sites. And what we have seen now through this NMR work, as well as some computational work and relating it to the catalysis, it appears that there's one particular site that is strained, shown right here, what we call this site 1, that appears to be related into improved reducibility in the system, as well as correlated with the activity that we have. So we think we have identified the site responsible for metathesis. So we're very excited about this. So to summarize then, I think from the open questions that I showed you before, we have some new insights as to kind of like how you form these active sites. We can reconcile the kinetics now in the field, or kind of what has been reported out there, and perhaps have a tool now to quantify the sites. And we're very excited then on what we can do now with these particular insights in the field. All right, so let's go with the second story. And this is a little bit different. And now we're going to move into the space of liquid phase catalysis with zeolites. And this is an area that we have been working on for several years. And that's because it combines some of the elements that we had kind of like from the PhD, right, on working on biomass conversion and some oxygenates, as well as some of the elements from the postdoc where I learned kind of how to synthesize some zeolites. And I'll tell you a little bit about this. So this is work that was led by John Diori, a great postdoc that joined the group, and Blake Johnson, also a grad student, and more recently Melissa and Babish, to try to figure out kind of like how we think about these elements. And this idea of solvent effects has been in our minds for a long time. And if you look at the literature, I mean, it's been known for decades and decades that solvents influence kinetics in many different ways. So we know that it can stabilize transition states, and they can do so in many different ways. There's a really interesting set of studies, both from Jim Dumesic's group and Dan Resasko's group, on thinking of using co-solvents and organizing small domains of clusters of solvents to accelerate rates in a particular way. There's also a very rich literature out there on how enzymatic systems structure, for example, water around the active site to be able to stabilize transition states. And then there's actually a very big body of knowledge as well that was generated on the zeolite side of things, for example, from Dave Flaherty's group and Raj Gounder, on how we think about solvation in confined spaces in the pores of a zeolite. Now, there's some challenges in all of this in that if we are trying to obtain a metric or a descriptor that is predictive of how this actually works, it's actually non-existent. It's very difficult to do. You know, some of the continuum models that we have, they're very inaccurate for polar solvents. The empirical correlations that have been developed, for example, in the work from Jim Dumesic, they're accurate, but they're limited to only specific regimes out there. We don't have a good way of understanding how these dielectric constants change as a function of confinement, for example. And dissolving interactions with the catalyst surface also is something that requires high-end calculations, for example, for us to really, really understand what's there. So we started working on, well, how can we think about this and paint a couple different pictures? Similar to what other people have done, we were painting this chemical picture, and we're trying to use transition state theory then to better understand the solvation effects and put it in terms of perhaps thermodynamic parameters. And looking, for example, of course, how these activities modulate the solvation of, say, the most abundant reactive intermediates, the transition state, as well as the fluid phase species. So the system that we worked with to try to now frame this with transition state theory is working with these Lewis acid zeolites. So in this case, we're using a beta framework. We like it a lot because it has a lot of synthetic flexibility. It has large pores, about 7 nanometers in diameter, and you can install these tetrahedrally coordinated metal centers that do not put a charge into the framework. So things like tin, for example, or zirconium or hafnium. So you'll be able to accept electron density. You can coordinate molecules, but again, there's no Bronsted acidity associated with them. These sites are isolated, and you can actually titrate them. You can identify them. And there's 3 types that we would like to study. We have the open site, which is a metal then that is coordinated to 3 silicon atoms through oxygens, of course, and then it has 1 hydroxyl group. So it's one of the bonds is broken. We have what are called closed sites. This is a fully coordinated metal center. And then, of course, we have the silanol groups around there. These sites, they're in the framework, they're isolated, and they're amenable to titration. So we can use something like a deuterated acetonitrile, and we can get very specific counts of how many of these sites of each one do we have. And these are methods that were developed, for example, in Raj Gounder's group, in Avellino's group, as well as ours. And these are very well-established protocols on how we can use infrared spectroscopy with deuterated acetonitrile to count. Not only that, but we can change or modulate the polarity of the system. So if we work with zeolites that are synthesized in fluoride media, we can make it very defect-free. But if we add some, for example, we start with an aluminum beta, we dealuminate, create some silanol nests, and then graft the metal onto that, you can actually modulate the level of metal content and the silanol groups. And then there's some reactions, that are probe reactions, that have been very well studied, where we understand the mechanism, we understand the energetics, and we understand more or less how it works. For example, this is an example of transfer hydrogenation reaction. This is converting a ketone to an alcohol, for example. And we know that the rates are strongly dependent on the solvent identity. We know that the open sites are responsible for catalytic activity. And we know many things about the mechanism, and I'll tell you that, a little bit more about that. So we began this investigation by trying to understand what is the solvation environment inside of these pores. So we started dosing into our hydrophobic materials a little bit of butanol. And you see here the progression of what happens, how the signatures evolve as you start to saturate the pores. What is important is that there's this signature at about 3,500 wave numbers that are associated with butanol dimers that are well arranged inside of the pores of the material. If you compare now the same experiment, but for the hydrophilic sample, the one that has a lot of silanol nests, you see that these signatures actually do not appear there, and instead you see that the butanol that is inside of the pores is fully disordered or liquid phase-like. And this is a very important parameter because then this is the picture that we have in our heads of what is going on there. Because of the pore being very nonpolar, you see that you have these ordered dimers that are hydrogen bonded inside of the framework, which means that there's some kind of order that you would have to disrupt whenever you adsorb a molecule. So if we start looking at our probe reaction, this is a cyclohexanone transfer hydrogenation with 2-butanol. You see that if you follow kind of like the cycle from the left all the way counterclockwise, we have a site that is fully covered with butanol. And then we have these adsorption events from the cyclohexanone. We have the transition state on the transfer hydrogenation, and then we release it. And we can make a kinetic model out of that. So we simplify it. We group the parameters that we cannot differentiate kinetically. We pick 2 most abundant reactive intermediates, this being the site that is fully covered with butanol, and then the adduct that has both reaction partners. And we use activities then to correct for non-idealities in the liquid phase. And we take a look at, well, how does the adsorption rate constant depends, right? So we're looking at this step, K2, and we're comparing the state between the adduct and the fully covered site. And then we look at the apparent rate constant, which is just what we believe is the rate limiting step, right? So this would be actually the transfer hydrogenation side of things. And we're looking at the difference in the free energies in those two systems. So now we run the reaction for the hydrophobic material, for the hydrophilic material, for different activities, so different concentrations of our reagent, and also different temperatures, and we fit the data, and now we can extract from there the apparent enthalpies and entropies of the reaction. So if you take a look at these 2 values, you see that it appears that for the hydrophobic material, we're enthalpically stabilizing that intermediate. In addition to that, if you now compare the adsorption rate constants, they're much more positive for the hydrophobic material, which tells you that, again, something is happening in terms of changing the thermodynamics of adsorption because of this ordering in the system. So what we think is happening right now then is for the hydrophilic material, we have a solvent, a liquid-like environment, whereas in the hydrophobic material, it's ordered such that whenever the cyclohexanone comes in, it actually disrupts that order. You get this enthalpic stabilization boost, but also you pay an entropic penalty on doing that. But when you put all of those 2 elements together, that stabilization effect allows you to now increase the rate by an order of magnitude on this particular system. So we're excited about that result because it gives us this insight that maybe we need, these hydrogen-bonded networks inside of the zeolite to accelerate rates, and we started exploring other solvents. So in this case, we looked at toluene, for example, as well as acetonitrile. So now we have an aprotic polar solvent. And the results were interesting in that with acetonitrile, it appears that you can stabilize a little bit better, that transition state, but the numbers indicate that now the system is very tightly coordinated, so you have to pay, again, these penalties to be able to adsorb and desorb the system. So in the end, really, we do not have a clear way to predict now what is going on inside of these systems, right? So this tells us that perhaps we need a different metric for us to try to understand how the solvation happens. And this brought us to think about a different picture of solvation. So instead of looking at the chemical picture that I showed you before, what if we were to look at it in terms of electrostatics? So when you put a molecule inside of a solvent, the solvent molecules around it will change their direction, right? So if you have something with a dipole, the solvent molecules around it will change and rearrange themselves to try to minimize the energy of the system. So now the solvent itself is not randomly organized, and because of that new orientation, you actually will create an electric field near the site. And that means that maybe we can recast this concept of solvation in terms of electric fields. So if you take a look at again, what is the influence of that electric field onto our rates? So we know that perhaps we can stabilize it. When you look at how the electric field influences the free energy of the system, it's actually related to the strength of the electric field and the dipole moment of the molecule, or the dipole moment difference, for example, between the transition state and the reagent. So now if you take that concept and you put it into the classic expression for taking a rate out of transition state theory, you will get this element or this number in blue. And as you can see then that you will have a promotional effect every time the difference in the partial dipole moments between the transition state and the reagent align with the electric field. And we can make a ballpark calculation of how important that would be or how relevant that would be. So if we take that difference in the dipole moment to be about 1 dBi, which is quite reasonable, you see that you can perhaps get an enhancement of an order of magnitude whenever you have an electric field of about 1 volt per nanometer. And those are electric field strengths that actually are accessible from solvation, or that would be accessible, for example, for electrocatalysis, from electrolyte and electroelectrolyte interfaces. So then we went into the literature, and there's a vast body of work out there on trying to understand now promotion of rates, but with biological systems. So for example, work by Stephen Boxer on the keto steroid isomerases, where the concept was that these residues would be able to orient and stabilize these electric fields in such a way that you can get a big promotion in the reaction rate. And what they did a combination of Stark spectroscopy with molecular dynamics to now correlate the rates with what the electric field inside that pocket is. So what we decided to do is to ask a very simple question. Well, is there a relationship between these two? Can we apply something similar in nature to how we did it or how they did it for the biological system? And without going in too much into the details here, I can tell you that there appears to be a very strong relationship then between the free energies or the rates of the reaction and the electric fields inside of the pores of this system. So we feel we have in our hands this metric that allows you to now probe solvation effects inside of the pores in a very unique way with a universal descriptor that might allow you to not only figure out how these reaction rates work, but actually predict activation enthalpies and entropies in the system. So I hope that we can continue working on that particular space because it's very exciting. All right, so we can go now to the third story. And I hope everybody's still doing okay. And the third story is actually inspired by, well, it's all together, you know, but we started asking a lot of questions about kind of like how do electrostatics influence kinetics? And this is something that we began discussing with Yogi Surendranath a few years ago in the Department of Chemistry at MIT, because we always kind of try to figure out, is there a common language of how we can join things or concepts in electrocatalysis with concepts in thermochemical catalysis? And in the end, this is all the same, right? They're all related in some way. But how do we unify this, and how do we exploit perhaps some of these concepts so that we can accelerate rates and promote catalysis? So the two questions that we wanted to answer is, well, how do we harness electric fields to influence thermochemical catalysis or non-faradaic processes, perhaps? And maybe more importantly, for us to be able to answer that first question is, well, how do we study interfaces that are disconnected from wires, right? So when we are working with a plug flow reactor with solid catalysts, there's no way for us to connect that as in an electrochemical cell. So we need to figure out methods of now probing, not only polarizing an interface, but then quantifying that extent of polarization and relating that to the kinetics. And that is something that is not trivial. But I showed you that for biological systems, this it has been studied, and it continues to be a very interesting field. There's quite a bit of work now also on molecular catalysis as to how these oriented electric fields actually influence rates. And what we wanted to do is figure out, well, how do we do this now for heterogeneous catalysts, both that are conductive and perhaps for non-conductive ones as well. And the way we did this was to think about it just from fundamental terms. So if you think about the electrochemical potential of a species, right? So this in the end, it comprises the work that you need to add like a particle to a particular system. And you will have a contribution, if the species is charged, you will have a contribution that encompasses the electrostatic component that has, the free charges and the dipoles. So then the interesting part is whenever you have now an interface, so when now two interfaces come together, they have to equilibrate, so the chemical potentials have to equal each other. And what happens then is that the charges have to redistribute, right? So that you can establish that chemical potential. So if your species has different affinities for the two surfaces, then actually you will have a spontaneous charge transfer and a spontaneous polarization of that interface. And what this tells you is that for any interface that you have there, regardless if it is connected to wires or not, for example, every time you have a liquid-solid interface, you will always polarize it. It will always be there. The question is that, well, we usually don't measure it, and we need to figure out a way of controlling it and measuring it. So the concept that we had is, well, if that polarization always exists, that means that perhaps we can have what we call this wireless polarization, and we can actually use it to quantify and study these effects. And with this, we started with this thought exercise. So imagine that you have water, and you deposit some platinum nanoparticles on it. And then you pressurize it with hydrogen. So you will establish an equilibrium where hydrogen will dissociate on the surface of the platinum. And in addition to that, you will have an equilibrium because there will be a deprotonation event so that you can have protons plus hydrogen adsorbed on the surface. And whenever it deprotonates, it leaves some electrons behind as well. So this system exists in this equilibrium, and if you particularly focus on the protonation-deprotonation event, you can actually now figure out, kind of like recasting the Nernst equation, for example. You can see, well, what is the influence of pH on the extent of polarization that you have, considering that the chemical potential of the adsorbed hydrogen and the electrons remains constant. And if you look then at this equation, it tells you something quite intriguing, that pH is a handle for you to be able to polarize that interface to a given extent. So for example, if you increase the pH of the solution, you decrease the chemical potential of your protons, and you will polarize the interface more. You will charge the interface with more negative charges in there. So this is actually quite unique because that means that you can now use pH, something that we can handle very well, to polarize any type of platinum-water interface whenever you have hydrogen around, as soon as that is equilibrated. So this means that now we have a new handle to track that polarization. So we can have a wired polarization, as you would have it in a classic electrochemical setup with potentiostat. Or now you have this idea of using pH, to do this. Or as I'll show you, you can also do it with redox buffers and doing outer sphere electron transfer to pin that potential. So in this way, you don't need to have the system connected to wires. It can be wireless. So now, how do we now quantify these effects? How do we track this? You can potentially measure this somehow with like a potentiostat to measure what is the potential. But the challenge when you're doing that measurement is that you cannot decouple the chemical and the electrochemical factors. The chemical and electrostatic factors. So we need something different to be able to probe how much we have polarized that interface. And in this case, we can use spectroscopy. So what we did, we set up an ATR cell, and we drop casted some of these supported platinum particles on carbon. And then we put in a thin layer of water, and we control the pH. And in this case, what happens is that you will take advantage of what is called the Stark effect. And imagine the Stark effect is like when you're looking at the vibrational frequency of CO, that frequency, the dipole there of the transition, is very sensitive to the electric field that particular bond is feeling. And you can observe it then with the IR. So this means that as we are increasing the polarization and we're going from an acidic pH to a basic pH, you see this red shift in the IR spectrum. And that's what is called this Stark effect. And this is something that is quantifiable. Not only that, but since, again, we're looking at kind of like this reversible hydrogen setup, you can measure the open circuit potential and now of the system, so with just external electrodes, and you can now associate the shift in the IR bands with that open circuit potential, and you see that the Stark shift is about 60 inverse centimeters per inverse volt, and it follows this Nernstian behavior in the system. So now we can either use the wave numbers from the IR, or we can use the measurement on the open circuit potential with an external electrode to quantify the extent of polarization in the system. And that is very powerful because, again, you now have a metric to understand that polarization in this wireless setup. So what we did then is to start with a probe reaction. We started with a system that we thought would be completely impervious to the role of potential. We thought, if we select something like ethylene hydrogenation, this is something that has neutral intermediates, absolutely non-polar, and it's structure insensitive. And we thought, well, this will be our control reaction. This should not actually change as a function of potential. But look what happened here. So what I'm showing you is the turnover rate as a function of this open circuit potential, or as a function of pH, right? You can think about it both ways, or as a function of polarization extent. And what we see is that as we increase the pH in the solution, we decrease the rate of the reaction. So we attenuate the rate. So over 11 pH units, the rate decreases by about threefold or so. In addition, since you can be measuring the open circuit potential, you see that this continues to behave Nernstianly. That means that equilibrium with the hydrogen adsorption and deprotonation is maintained in this system. Now the question is, maybe this was just a pH effect. What if it was water, it was something else? We don't know. So we needed to figure out an orthogonal way to polarize our interface. So we did it with pH in water, but you can also use redox buffers, as I was telling you. For example, you can have a completely non-polar solvent, like orthodifluorobenzene, and you can add these metallocene and metallocenium mixtures. So these mixtures actually will have a very specific redox potential, and through outer sphere electron transfer, they pin the potential of your surface to that value. So then now you have a completely different mechanism by which you can polarize the interface. So in this case, we have no proton donors at all in the system. And when we measure now this as a function of open circuit potential, again, this behaves as expected. It behaves Nernstianly. And look at what happens here. So now we have two different ways of polarizing the interface in completely different systems, and we're getting attenuation rates that are very, very similar. And to us, this was absolutely mind-blowing, because you have a system that is water versus an aprotic solvent, proton versus electron transfer, hydrophilic versus lipophilic cations that we use to run these reactions. Nonetheless, the attenuation of the rate is very similar for both cases. So what we think is happening is that we have this general phenomenon where the electrostatics are actually influencing the catalysis in a very unique way. And we're building up kind of like a thermodynamic platform for us to understand that. But something that is very neat about this is that now you can traverse a wide range of potentials. And you see that the maximum in the rate, for example, for ethylene hydrogenation, happens very close to the point of zero charge. This is where the solvent is most disorganized. And it actually approaches the gas phase ethylene rate. In this case, it's not because of side blocking. Our orders are still positive. We kind of have done all the tests to check that this is not because of some kind of side blocking event. And then when we run the reaction with a larger molecule, a larger olefin like butene, you see that the maximum in the rate is also near the PZC, but it's a stronger attenuation. So it's about a twofold difference in the influence of that potential on the rate. So what we think is happening, the picture that we have painted in our minds is that, as you polarize the interface, the solvent molecules align themselves to compensate that charge. And as ethylene comes in and absorbs onto that surface, it displaces the solvent. But to maintain equilibrium, the electrostatic equilibrium, it has to donate or receive some charge, depending on what side you are of the PZC. So this idea of electroabsorption valency and this activation of charges, all of those concepts become very, very important in trying to understand this phenomenon. Oh, yeah. I'm sorry. And lastly, the last set of things that we asked is, all that I showed you before is all on conductive interfaces. So we're polarizing, and a question that we had for a long time is, well, if we're using a support that is an insulator, something that does not allow you to perhaps polarize evenly, would this effect still hold or not? So now the challenge is that when you have an insulating support, all the methods that I showed you before would be very difficult to implement. So we can still do the Stark spectroscopy, and we actually observed very similar Stark shifts, but we don't have a way of quantifying it the same way because we cannot now measure those potentials with electrodes. So what we did then is we took advantage of ambient pressure XPS and some new instrumentation that is out there that is absolutely mind-blowing as well. And the idea here is that, XPS gives you a sense of course, the identity of the metals that you have, but it also allows you to probe the local potential of that particular system. So the idea here is that whenever we have a liquid interface or a solid liquid interface, then the extent or how difficult or the amount of work that you have to do to eject that photoelectron from the surface through the liquid layer all the way to the detector is a direct measurement of that potential that is around that particular site. So what we did then, we worked with Ethan Crumlin at LBNL, and he has this amazing setup where you can actually probe solid liquid interfaces with ambient pressure XPS. So you take a pellet, for example, you create you spot, for example, your platinum or your gold. In this case, we're looking at zirconium or zirconia as the support. And you dip it into your solution of different pHs. You take it out. I don't think I have a picture here, no. And then you do your experiment. You probe it. You have to do, it's a very difficult problem. Carl Wessendorf has a talk on this tomorrow. If you want to see the details on this, it's actually a very, very difficult experiment. But the results were spectacular, So what you're looking at here is the platinum 4F binding energies as a function of pH. And what we observe is that as we polarize that interface stronger, so that is as we go to higher pHs and the system is more negatively charged, you see that the binding energies go down, right? They decrease. And we're telling you that the Fermi level increases, right? Because you have kind of like more negative charges in that particular system. But not only that, but again, the system behaves inertially with this slopes of about 66 millielectron volt per pH unit. So not only for platinum, but this is very similar for gold as well. So this tells you again that even gold at these conditions is able to maintain that equilibrium whenever you are in the presence of hydrogen and as a function of pH. So you can pin the potential of gold on zirconia or platinum on zirconia very similarly to how we did it for platinum on carbon, for example. And this is very important because this tells you that this effect of polarizing the interface is universal. And you can do it for things that are not conductive. You will always have it. So in terms of the takeaway message then of this work is that spontaneous charge transfer happens at all of these interfaces. It's always been there, but we have never been able to fully quantify it. And this is something that we really have to consider, probably the same way as we track temperature, we track concentrations, we track pressure. Tracking this potential for liquid phase